Okay.
I need that thing.
Oh, crap. Oh, gosh. Yeah, I'll just drag it.
Okay,
Hey.
nice. Okay.
Okay.
So.
So share screen. Okay.
We're screen sharing. Also
Yeah.
muted.
Yeah. No, this I'm recording. I'm
Oh, okay.
Yeah.
Yes.
This is right. Hey.
Okay, so sorry for the technical delays. My name's Lawrence, and today I'll be talking about large language model compression. So a bit about me. I'm Lawrence Liu. I'm a first-year master's student. I did my undergrad here from 2021 to 2024 in electrical engineering. Best major. And and I'm currently doing research with Professor Lin Yang in the EC department. And primarily I'm doing actual model compression and discrete optimization. So this talk should be fairly in line with my research. Okay, so let's start with a motivating example. So let's consider Llama 3 8 billion. So 8 billion parameters, if we use the naive 32 bits for each parameter, that would be roughly 32 gigabytes of memory needed to just for the parameters itself. Therefore, for fast inference, we would need at least an RTX 5090, assuming you could get your hands on that. And so therefore, we can see that naive inference is very expensive. So the question, therefore, is can we reduce the computational cost of inference without sacrificing that much performance, hopefully to a point that we can actually fit these kinds of devices on phones and those kinds of edge devices. Okay, so there's a couple quantization strategies. So intuitively, there are two ways of doing it. We can either reduce the number of bits we use to represent each parameter. That's what we call quantization. Or we can just start removing parameters. So there's several ways of doing this. The first is we could just start removing parameters, which is called pruning. Or we can represent each weight in a low rank format. So this is what's known as low rank compression. And we also train a smaller model to replicate the behavior of a larger model. This is known as knowledge distillation. And because for this talk, I'm going to focus on few to zero shot compression. So without having to do complicated retraining for the most part, I'm going to ignore knowledge distillation, also because I don't have enough time to write the slides for that. Okay, so let's start out with a simple approximation. So let's let delta W denote a small perturbation in the weights. We can approximate this as basically compression here. So then we can take the Taylor series expansion of the loss. We ignore terms higher than 2 because we assume delta W is small enough that that's possible. So then we're left with the following Taylor series expansion. If we assume the model is well converged, then this gradient term will vanish because it will be close to 0. Okay, so let's consider. So a common thing that you'll see in a lot of compression papers is because of the large number of parameters, optimizing over the whole entire model itself is very hard. So instead, they will focus on a linear layer by linear layer proxy loss. So in a sense, where W hat is the quantized or compressed W, W is the original, X is the input activations to this layer. And then we can write it out as this using this sort of a Hessian, which we approximate by sampling a bunch of samples from a calibration data set. So for large language models, this is usually like red pajama 1 trillion. And then we just take that. We just do basically the same thing. I'm missing a normalization factor, but that's that gets lost. The thing is, actually, this is somewhat expensive, especially for state-of-the-art compression techniques, and will require the N samples will be roughly around 25 million tokens, which computing it for models such as Llama, such as a 70B parameter model, takes actually quite a bit of memory in and of itself, around 700 gigabytes of RAM. And I will discuss some strategies later about how to negate this. Okay, so now, yeah, go ahead.
What's wrong with literally just trying to optimize and say, oh, I want the weights to be the same afterwards as well? Like even when I, just like I turn down the number of bits that I used to code my weights, and I just do like a few more optimization runs of like, oh, I want the output so to the same.
Like by you tune down the number of bits, you mean just
like say you train with 32 bits, and I say I quantize all the way to 16 bits or 8 bits, and I just say, okay, I want my outputs to be the same, or my weights to be the same, so I can do some like optimization on that.
Most people have pushed beyond 8 to like 4 bits,
Right?
And at that point, there's only like 16 possible values, so it's a much more discrete problem, and you can't kind of assume that it's a continuous space where by using gradients you can easily hop to like the next value.
I see.
Yeah, so pruning. Okay, so there's several ways of pruning. The simplest way is what's known as unstructured pruning. So this, we literally just start zeroing out the p percent or n percent of the weights by some kind of criterion. The main problem with this, so this has actually fairly minimal performance loss, which is a fairly interesting thing, because even up to 50% pruning, the model still retains most of its original performance. The problem is that because the mask is unstructured, the memory access pattern during inference will be unstructured, which means that for GPU speed up, it's not possible because GPUs rely on a heavily structured and parallelizable memory access pattern, right? To be able to parallelize it over its, very many threads. So currently there's no real world speed up or memory overhead reduction because they, in papers that actually do this, they actually just represent the maxed out ones by 0, which doesn't save you anything in the real world circumstance. So this is purely theoretical. But there is something known as N by M structured, semi-structured pruning. So what this basically enforces is from every M parameters, N of them have to be knocked out. So this is a much more structured memory access pattern. And actually, NVIDIA, the Ampere architecture for, I believe, the A6000 and A100s supports 2-4 semi-structured pruning. But the problem is because this enforces a pattern onto it, the performance loss is significantly higher than unstructured pruning. Yeah, so let's talk about 2 fairly classic papers. Yeah, sure.
Why does having it be structured in this way impact the performance that much? Because like if I feel like even for the randoms, like you're still like relatively random-ishly removing the weights. Why does having a constraint there impact performance?
Because it's basically it's a constraint on the optimization, right?
I see.
So in a sense, it's always it's going to be worse simply because of the constraint. And really, actually, what pruning will somewhat do is there will be some entire rows where it will only retain a couple weights. Okay. And this completely prevents that because it has to be every 2 of 4.
Oh, so because the one before random, you're thinking which weights you're zeroing out by optimization.
Yeah.
You can actually be like, oh, like this circuit isn't doing anything.
Yeah. So whereas this is structured, so and like for instance, 4A, which may be supported in the future, performs a lot better than 2-4 because you can have much more combinations of where the.
How do you actually represent constraints like in
in optimization, it's actually fairly simple. So they would just if you have like a score for each weight, if in a unstructured setting, you just pick the weights with the lowest score.
I see.
But this and you just pick the lowest two out of every four weights.
I see.
So yeah, so what optimal brain surgeon does is we go back to this Hessian. And we enforce a constraint that we zero out parameter Q. So this is where this delta W times EQT. This is EQ is a one hot vector at index Q. So then we minimize this. We can write it as Lagrangian, and then we can solve it to get both what's the optimal update for the remaining parameters, as well as what is the what is the increase in the Hessian loss derived from by zeroing out the parameter. So then we can just simply start picking parameters by picking the ones with the lowest this, and then after we zero them out, we then come back and we recover back some of the performance by updating the unpruned parameters. So this is what sparse GPT does. They do it in a slightly different format where instead of going over the whole entire weight matrix, because for our LLM that's very big, they go over it in blocks, and then each block they pick 50% to remove, then update everything beyond that block, and then come back and do it again. Go ahead.
Just to clarify, how is this different from like randomly removing the mask? Because like they kind of look similar to.
Oh, sorry. It's not random. So this is unstructured. But it's still by a certain criterion, and this is the criterion we are using.
Also, is this mask like similar?
Yeah. No, this mask is unstructured, because you can see there isn't really that much of a pattern between each thing.
So what does the semi-structure?
This is a semi-structured mask. So you can see that this is every two of every four are removed. Ours white are removed once. So you can see, for instance, of these four, two of them are removed. Here, two of them are removed.
Sorry, I can't really clearly see the red borders. Like, is it like 4 in a row?
Yeah, 4 in a row, basically. Yeah. Okay. The main problem with this is that we have to do this inverse of the Hessian, which is very complicated. There are some tricks that we can play to make it faster, but still it's a pretty expensive computation to make. So what some people do is they actually found that actually we can just assume that the Hessian is diagonal. And if we assume that, then this kind of, first of all, we lose the update on the remaining weights. That gets zeroed out. Second of all, this, an equivalent way of writing that is this, we're missing some square root factors, but that's completely fine because that's a monotonically increasing function. And then you can just simply prune by selecting the weights with the lowest score, and then just zero out those weights without updating the previous weights. And we still actually get performance that is comparable to, if not better than, sparse GPT. So this is what the Wanda paper does. And an additional benefit of that is actually because we don't rely on computing the whole entire Hessian, we have a significantly lower dependence on the number of calibration samples we have to sample, which makes pruning a much better thing. But you can see, so here are the main results between, this is zero shot. But this is the main results between sparse GPT Wanda and just simply pruning by magnitude. We can see that basically the performance drops off significantly at Q4 pruning, which is, as I talked about, is really the only one that we can actually implement on devices in a real world circumstance. And second of all, this type of pruning really only gets us 50% reduction, which isn't actually as much as what we can do with quantization. So the third way is what's known as structured pruning. So for structured pruning, we just start removing rows and columns, and eventually some papers actually just start removing entire attention heads and layers. So this has the most important part, because this is basically just making your weight matrices smaller and just doing less multiplications. But I didn't finish the sentence, sorry. But basically the performance loss in this is a lot worse because it's very structured compared with unstructured and semi-structured pruning. And actually a lot of papers, after they do this kind of structured pruning, they will come back and do like a low rank fine tuning to try to recover back some of the performance. Okay, so quantization. So fundamentally, what is quantization? So quantization will be represented with less bits, as I talked about. So for example, for 4-bit quantization, we have, as I talked about, 2 to the 4 or 16 possible values for each weight. So modern quantization really consists of 2 things, especially at these low bits of like 4, 3, 2, and even 1. So we map each weight. So if we're doing k-bit quantization, then we map each weight to a k-bit code. This is discrete, and this is hard to optimize. So this is the main challenge in quantization. And the second is a lookup table, or an LUT, where we map each k-bit code to a floating point. So the simplest quantization is what's known as round to the nearest quantization. So what this simply does is we have a scale factor, which is usually just the minimum and maximum weight in the weight matrix. And then we just do a linear, we have a linear code book, linearly spaced code book, uniformly spaced code book, sorry. And then we just round it to the nearest possible value in that code book. So the question is this optimal? Well, if we return back to, this kind of Hessian loss, if we pick a simple Hessian that has 1s on a diagonal and 0.5 on off diagonal, we see that the approximate increase in task loss is this. Round to the nearest is possible if we ignore the off diagonal aspects. So if we ignore this term. However, if we do actually consider that, actually we can improve on this. For example, you can see that if we just change the signs, the rounding error signs, we can actually reduce the task loss significantly, since this will now become negative. So we're subtracting from it. So one of the first papers to do something about this was called AdaRound. So this is from 2020. What basically they do is they just do a soft quantization by basically flooring it, and they add this 0, 1 bounded thing to either round it down or round it up. And this is basically the sigmoid, and we scale it slightly to prevent losing gradients at the far edges. And then we clip it again to go back to 0, 1. And then what they do is they add a regularization term to try to force these soft roundings towards either 0 or 1. So how they do it is using this, and they anneal beta. So they start off with a very high beta, which is largely flat, and that allows for more shifting. And then slowly, as they train, they push beta towards 1, which kind of forces the values apart. An important thing to note is that we're not optimizing this. We are just optimizing this V, which indicates which way we should round, basically up or down. Okay. Any questions? No. Yeah, go ahead.
This again.
You just clip it between 0 and 1. We do this basically because sigmoid, the gradients are 0 at the edges, which is what we don't really want. So we scale it up to from basically from negative 0.1 to 1.1. Yeah, go ahead. Yeah, and V is basically because this makes, so V transforms to something between 0 and 1, right? So that is basically whether we should round down or whether we should round up, right? Because if we round up, then this would be 1 because we're flooring it. And then if we round down, then it should be 0.
Oh, so like basically it's like every single iteration, you're doing your quantization.
Yeah,
And then you have this correction term that says should I round up or round down?
Yeah.
And we're actually optimizing for trying to learn is that correction term.
yeah.
I see.
And then but that one largely focused on vision models because that was from or CNNs because that was from 2020 before LLMs became really that big. So one of the first papers that did this for quantization was GPTQ. So they used the same format that was done for sparse GPT, but instead they generalized it to quantization. So if you'll note, this term is actually very similar to this term right here, except for we have an additional, instead of 0, it's the quantized version. So doing that, they basically do the same thing, where they go they go in a block, and after they quantize a block, they update the remaining weights to try to recover some of the performance. And then you can play a trick to because the main problem is with this is you would have to, for every single row, you'd have to recompute the inverse, which is very complicated. So instead, you can play a simple trick to only have to do the inverse calculation once, and that's that. Okay, there's a couple problems with this kind of quantization. The first is there are some outliers. So there are some values in the weight matrix that are very, very, very large. So this is the relative absolute weight value. So we can see that like around 99% of the weights will actually occur in a range that's much smaller than the 100% range. The second problem is there are certain weights that are just very sensitive, and if errors on those weights have a very disproportionate impact on the performance loss. So if we could A, minimize the quantization error for those weights, and B, kind of suppress or represent the outliers in a different manner, we can significantly improve our quantization. So this paper, active weighted quantization, does that by basically scaling the weights and then scaling the inputs to reverse the impact of scaling the weights. And what this basically does is because some input channels, the weights for those channels have very high magnitude, it scales those down so that the range is much smaller, so it makes quantization easier. And then how they optimize it is fairly simple. They just do a grid search basically of all the possible scalings between 0 and 1, because rounding doesn't preserve gradients, so we can't use standard gradient descent. And then yeah, they just do a grid search, find the one that minimizes it. Another paper, and I really like this paper, is squeeze out LLM. So they take, first thing they do is they take a slightly different way of approximating the sample HCM. So instead of sampling a bunch of calibration activations and then calculating the update, the outer product, they just calculate the gradient on a data set, take that outer product, assume that it's diagonal, which, okay, go ahead, and then basically boils down to a weighted k-means, right? So you can view the quantized values as the centroids and these FII as the weights. So what they do is literally just weighted k-means, and they show that the distribution is much more clustered around their so-called sensitive values in red. So we can see that the above is the actual distribution of weights. Below is the quantized distribution. And then so green is the uniform scale, uniform code book. And then purple is their so-called what do you call it? Is their k-means code book, which is much more clustered around these sensitive weights. Okay, so the second trick they play is a sparse plus dense decomposition. So what I said previously about unstructured being not having a real world speed up is only true for if we keep more than 1% sparse. If we go below 1%, we start seeing savings in just simply, even though the memory access pattern is unstructured, because of the number of computations we need to do is so little, we actually start seeing an improvement. So what they do is they just keep the tiny percent of outliers. In this graph, they say less than 1%. It's more like around 0.5% of outliers in a sparse matrix. And then the rest is represented in a dense matrix. So this basically, because now this dense matrix has significantly less range, it's a lot easier to quantize if accurately. So you can see that they get a very significant speed improvement over both over GPTQ. The thing is, so I come from, both me and Professor Yang come from a background of reinforcement learning. So in theoretical reinforcement learning, we like to have bounds and proofs over things. So one can ask, is it possible to get bounds and proofs over quantization errors? So yes, it is. And this paper, Quip, does that. So basically what they do is they describe a form of linear feedback round. So basically after we round one value, we use the rounding error, and that's linearly fed back to the unquantized values. So we can represent it in terms of this, or in terms of this, where U is a strictly upper triangular matrix with columns of AK. And what they show is that the optimal U is derived from this LDL decomposition of the Hessian. And then from this, they can actually get bounds on the average and worst case error. And they can show that this is worst and average case optimal. So the second thing is what's known as mu incoherence. So what does mu incoherence do? Basically, what it does is for a so it bounds the weight values to be distributed less than mu times the Frobenius norm divided by the input and output dimensions. So this effectively ensures that the weights are distributed in a Gaussian manner. The second is mu incoherence for the Hessian, which is basically saying that the eigen decompositions values are also bounded. So why do we care about this? Well, for weights, it ensures it's Gaussian distributed, which is good for quantization. For the Hessian, it actually allows us to put a bound on the trace of D, which, if you'll note from the previous slide, is what our worst than average case quantization error is around. So then, if we can enforce mu incoherence, we can force this to be we can provide an upper bound on the quantization error. So the question is, how do we do it? It can be shown that if we multiply the Hessian and the weight by two random or orthogonal matrices, we can get something that is mu incoherent with high probability. And the nice thing about orthogonal matrices is that if you multiply it by its transpose, it reduces down to the identity matrix. So we can from our original problem, we can just start multiplying things by these orthogonal matrices and preserve the same optimization criteria while making it mu incoherent. The problem is, how do we generate and save these V and U without significant memory overhead? And also during inference time, it's without that much of a cost. So what they do is they basically define they basically define U and V as basically random sampled from a bunch of smaller orthogonal matrices, and then they do the Kronecker product. Sorry, and then you can be shown that both of these are mu incoherent in O tilde 1 time. So and then furthermore, for inference, we can get the additional overhead in terms of flops is only by n square root n. So this is scale significantly smaller than the actual n times n that we need for multiplying by the weight matrix itself. So this is not a dominant term, which is very good. Any questions? Yeah, go ahead.
So which one of the quantization algorithms do people actually use?
Squeeze or GPTQ, honestly. But as we move on towards like 2-bit and 1-bit quantization, then they start using some other algorithms, which I'll talk about.
Oh, okay.
Okay, so to a large extent these days, 4-bit quantization is what's considered solved, and most model inference is done in 4-bit quantization, and that's already an enormous speed up of roughly eight times less memory than naive 32-bit inference. But the problem is, can we reduce it by, say, another factor of 2? So if can we get down to 2-bit or maybe even 1-bit quantization? Because that would save us another enormous amount of memory. So for instance, for a 70B for a parameter model for 2-bit, we can get around 17.5 GB, which is pretty close to accessible for high-end consumer GPUs. And if we could reduce it to 1-bit, then we could get this down to around 8 bits per 8 gigabytes, which is accessible to most GPUs these days. The problem is beyond 3-bit scalar quantization really starts to break down. For example, for Llama 1 7B at 2 bits, the complexity on Wikitext 2, which is basically a measure of how how confused I'm. Is 2.1 times 10 times 1,000. Compared with for 3 bits right here, so for 7, it's only around 9, right? So this is enormous. It just starts blowing up below 3 bits. Yeah, go ahead.
I have a question about like super duper low bit quantization in general. So like when you're dealing with quantization like this, is it only the model that's quantized, or are your activations also quantized?
So primarily what most people have been focused on is model quantization, but there's also some research on
so your activation are still like FP16 or something?
FP16, yeah.
Okay.
And then during inference, they'll actually like
inflate up?
Yeah, they start like looking at tiny bits of the quantized weight matrix, inflate that tiny bit up to 16 bits, multiply,
operation,
yeah,
and put it
and then
back.
put it back,
I see.
and then start. But there is some work doing on both activation but that can only really do about 8 or 4-bit.
I see.
There's also some stuff with KB cache compression, but that won't be.
So basically, the quantization is really about how can I run this with less memory instead of how can I run this faster? Because I guess a lot of GPUs don't really support like really low.
Actually, even with only weight quantization, there's actually still a speed up in terms of inference. I'm not exactly sure.
Like you're still doing all your math in BF.
Yeah.
BF16.
Apparently, it's because you avoid certain memory bottlenecks, and then you're actually spending the full blown compute and not waiting for stuff to get loaded. And so it's actually like around 1,000%. Yeah, that 1,000%. Yeah, for 2-bit quantization. assuming, of course, you can fit the lookup table in the L1 cache. If you're not, then you start losing.
Right. Look at the table as in like, if I have this 2-bit quantization,
Yeah.
what floating point does it
Yeah,
correspond to? I see.
exactly.
That makes sense.
Lookup table usually is not like significant in terms of size.
For scalar quantization, it isn't, right? Because for 4 bits, it's only 16 values. So 16 values times 16, that's only what's it, 256. Yeah, I should know this, but yeah, it's only 256 bits, right? And compared to a whole entire weight matrix, like even for like 7B, llama 7B, that's around 16 million parameters, right? So it's completely insignificant. I'll talk about vector quantization in a bit, and actually for that, then that's where the lookup table starts becoming a very non-negligible overhead. Yeah, so what is vector quantization? So basically, instead of quantizing each parameter independently, we quantize groups of D parameters. So we map each of those vectors to a K times D code. And then our lookup table is a lookup table of each K times D code to a D-dimensional floating point vector. An important thing to notice here is that this actually allows us to do non-integer levels of quantization. So for instance, we can do 2.25 bits by simply for every 4 values, we represent it using 9 bits. So what is the benefit of this? Well, it allows us to shape the codebook to the weights. So for example, this is a 2D distribution of weights. So we can see for uniform quantization, we get this nice rectangular grid, right? But if for a large part our weights are somewhat close to a Gaussian distribution, this is not a very good use. So each of these would still take up, so each combination would still take up 8 bits. And this is not a very good use of our bits, right? Because it's not very often used. And non-uniform quantization, it's still a grid pattern, but we can still kind of force it more towards the center where there's more where the distribution is the highest. And then for like 2D vector quantization, you can see that it shapes much better to the distribution. Okay. So some of the first papers to do this was GPTQ and VPTQ. So they are pretty close to the same thing. And basically what they do is they extend the GPTQ framework, which is largely used for scalar quantization, to vector quantization. And they initialize the codebook through weighted k-means, basically, of the Hessian, similar to squeeze-out LLM, with a couple of differences. And then after they quantize using GPTQ, basically, then they kind of optimize this codebook by minimizing this where Q is the quantized weights. This is a convex problem. So you can solve it using convex solvers. And then a couple more recent papers is AQLM, or additive vector quantization. So what this does is it quantizes it by adding up several codes together. And the codes are selected through beam search. And then afterwards, they also do k-means initialization. And then after they do this kind of quantization, they again update the code book in a similar fashion to either GPTQ and VPTQ. So another one is called QuipSharp. So this one is basically this one's from the same authors as Quip, and it's basically an extension of Quip to vector quantization with a couple of improvements. The first is instead of using the Conquer product for type thing to get the orthogonal matrices, they use a Hammer transformation, and this allows us to save in both inference time overhead, because now it's n log n versus n square root n previously. and as well as getting tighter bounds for the mu and for the Hessian and weight matrix in coherence. And the final thing that they do is they do the a lattice coded code. So why do they do that? Well, they do that for one main reason. So as I said, the code book maps every 2 to the k times d code to a d-dimensional vector. And as you mentioned previously, you asked about previously, for scalar quantization, this kind of code book has very minimal overhead. Because if d is 1, then this is basically just 2 to the k, which really isn't that big for like 4 or 2-bit or 3-bit quantization. However, for if we're doing vector quantization, we have this additional factor of d. A number of bits we need to represent is this the size of our code book times the number of vectors times 16, because we're represented in 16 bits. And as I said, for fast inference, we need this to fit in the L1 cache of a GPU. So for A6000, it's around 128 kilobytes. For A100s, this is 192 kilobytes, if I remember correctly. So this basically bounds us to k times d has to be roughly less than or equal to 12. So the problem is this kind of the improvement of vector quantization over scalar quantization comes from high dimensional, which allows us to shape it better. So we need to find a better way of representing it that avoids this kind of exponential growth with d in order to have good or even better quantization. And then an additional point is that because there are 2 to the k times d codes, so for each d-dimensional vector we're quantizing, we have to search through all 2 to the k times d number of codes, which so therefore as d increases, the quantization time taken also increases exponentially. Okay, so now we'll move on to more, so we say exotic forms of quantization. So this is a fairly hot topic of research. Now, one very recent paper, this was New York Spotlight this year, is QTIP, or quantization with trellises and incoherence processes. So this is from the same group as Quip and Quip Sharp. And what they do is basically they use a trellis. So what is a trellis? A trellis is basically a directed graph with 2 to the L nodes, each of which has 2 to the KV input and output edges, and a value in RV associated with it. And then so if we quantize the sequence length, a sequence of length t, we can do this in linear time with respect to t through the Viterbi algorithm. This is the same Viterbi as from the engineering school in a certain other university in LA. And so this is an ancient concept from the 90s. So this on here, we can see a description of a trellis. So we can see that so this is L is 2 in this case. So we have 4 nodes. And then for each node, we have 2 possible walls to the next one, so on and so forth. The thing is, so then if we are doing so to have an analogy between this and vector quantization, if t is our dimension of our vector, now we can do quantization in linear time, basically, which is a significant speed up. What are the problems? Well, the main problem is that we still need to store the trellis and code. That still is exponential in terms of the size. And the second thing is that because this trellis is a graph, and we have to start from the starting point and do a walk through the whole entire graph, we can't do parallelized GPU decoding, which is bad because then there goes all of our inference time speed. So their solution is to use a bit shift trellis. So basically, the encoded bits themselves are storing the trellis structure by overlapping L minus K bits. And then to avoid having to store the lookup table in the GPU, they just use a lookup-free Gaussian code, where basically you do bit transformations onto the code itself to recover back a point that is distributed on a Gaussian. Okay, so some additional topics in quantization. The first one is, can we unify pruning and quantization under one framework? And so this is a very recent paper. This is a paper that I wrote. But basically the answer is yes. And the key part is we have this very novel normalization factor where we normalize basically along both the input and output. And furthermore, this has very minimal impact, has only a linear impact on inference time overhead. So we're compared with n log n for Flip Shark. And our objective is inspired by Wanda with some slight changes, but this is extendable to both quantization and also pruning. And then so this decomposes to weighted k-means for quantization, similar to squeeze GPT, squeeze LLM. But the key thing is, unlike squeeze LLM, we don't need to do a backward pass to compute the gradients. So this can be done zero shot. And in greedy picking, we just pick the lowest 2%. A couple interesting points about this one is that, first of all, this kind of normalization does something very similar to Quip's mu incoherence process. And that on this side is the weight pre-normalization, and this is the one post-normalization. So it distributes it in a ball shape, which is good for quantization. The second of all is Wanda prunes, as I mentioned, by output group basis. So basically, among each output channel, they prune P%. Our normalization actually does a very similar thing to that without having to enforce the P%, without having to enforce the output grouping. And we can see by results that we are able to outperform QuipShark while using 48 times less calibration data, as well as getting results that are comparable to, if not better than, Wanda and sparse GPT for pruning. Okay, the second topic is, after quantization, can we globally fine-tune the quantization to recover back some performance? The main trouble with this is, I mentioned, quantization introduces a discrete aspect, which is hard to optimize because we can no longer use gradients to propagate backwards. So the most basic form of this is to say, screw the discrete aspects, we're only going to fine-tune the continuous aspects. So that would be the code book, or like scaling vectors. And there's a couple ways of doing this. You can either do this layer by layer and minimize the mean squared error, which has less computational overhead, or we can just do end-to-end fine-tuning and minimize the KL divergence. And we can see that for extreme bit widths of around 2 bits per value, this has a very significant impact on the performance loss. The question is, can we do this? Can we go further? And the answer is yes. So this is PV tuning. This is a paper. This was NERP's this year oral. And basically what they do is they say we want to minimize phi, where phi is a bounded function in our machine learning model, or LLM. And then x is some parameters. And then we enforce that it's quantized by basically saying that while it can be in d-dimensional, the total number of possible values that it can take is only c. So c is the size of our code. Then we can define some partitions, where basically a partition means that they are mapped to the same value in the code. And then we can introduce this delta ij notation. And from this, basically, we decompose it into 2 steps. The first is the unconstrained continuous parameter optimization. This is easy, and this can be just done with Atom or any sort of your favorite gradient descent algorithms. The second is a discrete optimization, where we, in a sense, we update the mappings. This is hard. This is hard because, as I said, there's no gradients, and doing a simple just a search over the whole entire subspace is exponential in the number of parameters, which is completely unfeasible for even a small size large language model. And the thing is, we can show that both of these will reduce the loss. And then so therefore, since we assumed previously that phi is bounded, this implies that the model converges. So then the question is, how do we do the discrete optimization? Since, as I stated, doing a search over all the parameters is NP-hard. So what we do is a linearized VSTEP, where L is the L constant from L smoothness, if any of you guys have heard that from math. And then we can minimize this with respect to X, and we can show that this is equivalent to minimizing this, where Y plus is given by this. So this is simply can be done through a greedy search of each individual parameter by itself. So we break the dependency of one parameter on the other. The problem is that low bit widths, that is oftentimes just YK. So there's no assignment updates. So then the solution is to only update a small section of the weights. And then that kind of forces L to be much, much smaller, which blows this term up, which forces it to assign it to a different parameter. And so this is the overall algorithm. And the results are actually very interesting. So at 1 bit per value, we can actually get models that are somewhat usable. So this is an enormous improvement over everything else. And in my opinion, is a very exciting area of research. Okay, so the final form of compression that I will talk about is low rank compression. So what is low rank compression? Well, low rank compression is we represent A and B with low rank matrices. We represent W with low rank matrices, and our total number of parameters is, instead of dn times d out, is k times dn plus d out. And our inference time, we also are able to reduce the number of flops. So therefore, we can have both the memory and computational saving. The problem with this kind of optimization is that we kind of have to assume that the matrices themselves have an innate low rank property, which is really only the case for certain matrices, and especially is not apparent in the feed-forward network of a transformer. So this is largely actually relegated to combining with previously discussed methods. For example, some people have tried to use low rank on top of quantization to try to recover back some of the quantization performance loss. Or for example, the paper that I'm going to talk about now, we combine it with a structured sparse matrix. So this is actually by some of my collaborators at Georgia Tech. And basically they introduced this kind of importance score, which is the magnitude of the weight multiplied by the gradient. And then they smooth it through an exponential moving average, or beta is a term, is a hyperparameter. And then you can sum along the rows to get column-wise importance. So then what they do is they iteratively over the while training, they just and then they do simple just SVD to decompose the initial low rank matrices. So while training, basically they start iteratively pruning the worst columns over time, following this kind of a scheduler. And then that's about it. I'd like to thank Professor Linier for the mentorship and support, as well as my co-authors Inesh Chakrabarty, Yixiao Li from Georgia Tech, Professor Tu Zhao from Georgia Tech, Mandy Wong from Princeton, as well as the people from my previous lab, Dr. Yupin Zhang, Dr. Tom Mosul, who I think some of you guys know, and Professor Wani Rachadri, as well as Professor Degavi for helping me somewhat or poorly understand trellis quantization stuff. He was actually very, very excited about trellis quantization because it relates back to some research he did back in his PhD in the 90s. But yeah, that's it.
So when you say that like the 4-bit compression is solved, do you mean like the loss is like negligible?
Yeah, in a sense, yeah.
Negligible as is there a number like 99%?
It's yeah.
Oh,
Like actually I'm not sure about ChatGPT, but I know quite a few other open source LLMs just do inference for it. Go ahead.
I guess another thing is like, one of the things that I always kind of think about when I look at quantization papers is it's kind of like a diminishing returns kind of thing.
Yeah.
It's like, is 4-bit just like enough at this point if you're like sort of what's it called? If your activations are always just staying at FP16 anyway. Because like my thought kind of goes to like, oh, we want to also make it run faster. So like as GPUs come up with, you know, better kernels where they actually are able to do these sort of, you know, like very specific type of like, you know, maybe like a 4-bit int times like a 8-bit float or something.
Yeah.
Like when you do stuff and if they have optimization for that, that makes it much faster. Like where is the sort of bottleneck right now in terms of both speed and memory? Like, and like how, like does that kind of relate to the whole like is that a thing that you guys are worried about, or
not necessarily, because we actually write our own kernels.
right?
And there's some kernel-wise speed ups. Actually, the main thing is basically quantizing to like 2 or 1-bit level starts to allow you to fit on smartphones without having to, you know, go to cloud to do the actual compute. So like Apple and those kinds of people are very excited about combining this with like mixture of experts and those kind of things to allow us to like, instead of, you know, having to have like ChatGPT on our phones and without having to, you know, type it and having to go to cloud and do the compute there. But yeah.
I see.
Anything else? Okay. No.
I guess
okay.
I guess one more thing. One of the things that we actually talked about last week when we when like our team gave us whole thing about like modern LLMs and all that stuff is we started to see a lot of like FP8 training.
Yeah.
How do you know like roughly how are people managed to do this during training as well? Because all this seems to be like inference time stuff.
I believe training. I'm not as familiar with your training. My understanding is it's are you familiar with the AMP stuff from Torch about you keep the weights in 16, floating point 16, but the gradients are in 32, and then you
like mixed precision.
Yeah, mixed precision. My understanding is it's somewhat similar to that, but the weights are now in 8.
I see.
And then, but the gradients I believe are still kept in 32, if I remember,
okay,
or something like that. I did see it in the DeepSeek paper, but I haven't actually looked at that.
Okay.
But yeah.
It's just not good to compress the gradient. You want to maintain as much of the gradient as possible.
Because gradients are very small and have magnitudes that's very hard to predict.
Yeah.
You can clip them, people clip them, but it's like if your grades are really small, just start clipping them, quantizing them. Sometimes you just get all zeros for grades, you're doing nothing.
Yeah.
It's not good.
Yeah.
And also like Adam starts to misbehave at floating point 16.
Yeah.
And like starts throwing names randomly.
Yeah.
That's fine. Anything else? All right. I guess I'll follow there. Sorry, go ahead.
so like at like 8-bit, it's still like continuous, but when it goes to 4-bit, it starts becoming discrete.
Well, really, they're all discrete, right, in a sense. Yeah. But basically, at 8-bit, it's 2 to the 8, which is 256, versus 4-bit, it's 16. So, like, you can see the possible numbers are getting much more further spaced apart. So that's what we really mean by getting discrete. But yeah. Anything else? All right. No.
Thank you.
But
All right.
we'll stop.
Yeah.
recording.
Oh yeah.
We have a reading group 2 weeks, right? I think.
You're only doing the one next week.
Yeah.
Oh yeah. Okay. Yeah. Okay. We have a reading group next week as well. Where I completely forgot about this. So yeah, very quick announcement. So next week we're gonna have a little reading group that's a little bit more like traditional type of reading group, where like instead of having like a seminar type situation, we're actually gonna be looking at papers and discussing them a bit more like roundtable style. And Will and I we're gonna be leading it, and it's gonna be a little bit more of like a